So now it is approaching 50, so maybe I can start. Okay. Uh, we are talking about the fundamentals related with the grinding process. And yesterday we talked about few things, but today primarily we'll be focusing on the factors associated with the grinding that significantly uh, determine or affect the performance of the grinding process as a whole. So, if we understand those factors, the way by which the various technical things related to the grinding are affecting the removal of the material as well as the surface condition, if we understand this aspect, probably it will be easier to understand the way by which the grinding will be able to produce the particular kind of surface or the kind of particular performance that is given by the um, grinding. So there are different performance parameters related with the grinding and the factors that are affecting the performance. So these are the two things you can say we'll be talking about. Okay, so let me share the screen. So important or extremely important affecting the performance of which affecting performance of the grinding wheel. So for that, what you have to see is grinding is performed by the grinding wheel. Okay, so most of the things which are related with the grinding affecting the grinding performance are associated with the grinding wheel itself. Then other aspects like the speed of the wheel or the speed at which the workpiece is moved. So relative movement is needed between the tool, that is the wheel, and the workpiece to ensure the removal of the material. So at what speed that this relative movement exists between the two, which is facilitating the removal of the material, is crucial or critical. You see, the surface condition, the flatness and the smoothness are significantly also determined by the rigidity of the system, how robust the system is. Like if the system is vibrating, then lot of irregularities, roughness, and the poor surface will be produced. The system must be robust. This is one reason, because the grinding is a finishing kind of process. Another reason is the wheel, which is having the heavy mass, is rotated at a very high speed, like say 2000, 3000, 4000, even 6000 rpm. So when the high speed grinding wheel, when it is rotated to maintain the sturdiness, to have the required stability in wheel motion, the machine must be robust, it must be heavy and rigid, it should provide the required rigidity. So as far as the grinding wheel is concerned, wheel technical parameters associated with the wheel, the first and probably the foremost is the abrasive, which acts as a cutting tool here. So grinding is grinding uses the multiple cutting tool, where thousands of the cutting edges will be working. Okay, so these abrasives act as a cutting tool during the grinding, and of course the removal of the material will be taking place by the shear mechanism only, like about which I talked yesterday. Okay, apart from the grinding abrasive type, so abrasive, like there are multiple types of the abrasives which are used, which includes like alumina, silicon carbide, cubic boron nitride, and diamond. So these are, you can say, in increasing order of the hardness, and these are not used for cutting all types of the material, because you have to see that the grinding, during the grinding, these abrasives will be coming in very close contact with the workpiece for removing the material, that too at a high temperature. So if any kind of interaction between the abrasive and the grinding wheel is taking place, then it will be forming some kind of the chemical layers on the surface of the abrasives, and that can lead to the faster deterioration of the abrasives. So there must be inertness between the abrasive and the workpiece. If the two are having affinity of any sort, then it is not good. So that you can say compatibility between the abrasive and workpiece must be good, and they must be inert. If there is any kind of the incompatibility or affinity in terms of the reactions with each other, then it will be degrading the abrasive and degrading the life, degrading the cutting ability of the abrasives very fast. I'll give example. Say the diamond, primarily one form of carbon. Okay, if we use it for cutting the iron based systems, then carbon having the good affinity with the iron will be forming, say, iron carbide. So your carbon structure will get modified, it will become softer in the diamond. So the diamond tool will become softer. That is why the diamond may be extremely good for non-ferrous metals, but not for the ferrous metals. So we don't use the diamond for cutting the ferrous metals. Okay, so there is a similarly in silicon carbide you have carbon, and which can interact with the iron also. So certain forms of the ferrous metals are not actually machined using the silicon carbide or the diamond, but the non-ferrous metals you can easily machine. So you can say need of the abrasive and the workpiece compatibility, that has to be seen. Okay, and this is seen primarily in terms of the chemical inertness. There must be chemical the abrasive and the workpiece must be chemically inert with respect to each other. Inertness, you can say. Okay, right. So this is one thing. So here if you see, there are certain types of the abrasives which are used for particular kind of the material. About this abrasive I will talk little later. Let me talk like what are the things we will be making a grinding wheel. So apart from the abrasives, there is it is called grit size, or it is basically the abrasive size of the abrasives. Okay, these can be very coarse, maybe say 800 micrometers, say, let's say that, or these can be very fine, say 80 micrometer. So all will be doing the different roles, different things. How these the grid size will be affecting, I will talk in detail about this later. Then the grade of the wheel. So grade, what is the grade? Grade is about how firmly the bonding between the abrasive and the bonding material exists. So if the abrasive and the bonding material are held firmly in the matrix, or abrasive is held firmly in the bonding material, then it will not be removed easily. So it may be good in certain form, it may be bad in some other form. So this grade also indicates the hardness of the wheel, suggests the bonding between the extent of bonding which exists between the abrasive material and the bonding material. Okay, so soft bond means the bonding between the abrasive and the bonding material is poor. Okay, let's say this is the abrasive and the bonding material is this. So this bond is poor, it is called soft. If the bond is strong, it will be termed as hard. Okay, then the fourth point related with this is structure. Okay, so how that all these are related with the wheel only. So structure means how closely the abrasive particles are placed or arranged in a wheel. Okay, so these can be open, means these are the widely spaced abrasive particles in a wheel are widely spaced like this. There is a large gap, or the spacing between the abrasives is very close. These are very tightly packed like this. So that will be the kind of closed thing. Closed means the gap between the abrasives is very close. So this is also called dense one. Okay, and this is called open or closed structure or dense structure. In dense structure, abrasives are very tightly, closely packed. And the lastly is the fifth important aspect related with the wheel is the bonding material. Means what is the material which is being used to hold the abrasives in a particular shape, which may be in form of paper, which may be in form of wheel, which may be in form of a small strip also. So there are a number of materials like rubber or metals or vitrified materials. So there are different types of the materials which are used to hold. So they also affect the performance of the grinding. All these factors are extremely important with respect to the performance of the grinding. So how do we check the performance of the grinding? So relative speed, under this only we'll have the different ways by which workpiece and the grinding wheel is moved. Okay, so the speed, it can be the rotational speed of the wheel or the workpiece depending upon the type of grinding, or it can be the linear movement which is being given either to the grinding wheel in form of in feed, cross feed, longitudinal feed. About these things I talked yesterday. So the rotational movement being given either to the workpiece or to the grinding wheel or to the both, depending upon the type of grinding being performed, or the linear movement being given in form of in feed, that is determining the depth of cut, or the cross feed to cover the entire surface area, and the longitudinal feed given to the workpiece primarily to cover the entire length of the workpiece. All these terms I will be explaining in detail using the schematics later. Okay, so going with the abrasives in detail, I will go a little bit in detail. So for cutting, for cutting the since the grinding is used for the for finishing the not just soft but very hardened materials also, like ceramics, carbides, hardened steels. So abrasives must be hard enough. So what are the properties that are necessary for a material to be used as abrasive in a grinding wheel? See, which kind of the material can be used as abrasive for making the grinding wheel so that the grinding can be performed. Okay, all the example I have already given you, the things like the properties that are important in abrasive to act as to perform the grinding effectively is the hardness. So hardness means if it is hard, then it will be able to indent. It will be able to penetrate under the sufficient pressure to the other softer materials. Okay, at the same time, the hardness will allow the retention of the shape. It will not wear out so easily and so rapidly. Okay, so hardness, after the hardness, the wear resistance, the how rapidly the shape of the wheel abrasive is modified. Say initially if it was this, so certainly during the grinding the size and shape of the abrasive will be modified, and mostly these will get rounded off and smaller in size. So not just the sharp edges will be rounded off or they will be removed, but the size will also be removed. So when the wheel abrasives wear out, the size is reduced, one, and they get rounded off. Okay, so both these will be reducing the cutting ability of the abrasives. Okay, so for good performance, longer performance of the grinding wheel, it is necessary that the dimensional change in the abrasive is minimum, and that is why the resistance to wear of these abrasives must be good. Okay, so so first is hardness, second is wear resistance, third is toughness. Okay, so the toughness means the resistance to impact. The material abrasives, although these are the two, hardness and the toughness, these are the two just opposite properties. So if you are having high hardness, the toughness will be low, but it is important for proper functionality, especially of the cutting tools, that the hardness, not just high hardness, but also enough toughness is there with the material which is to be used as a cutting material, whether it is a single point cutting tool or milling cutter or drilling or the drill or anything that is being used for cutting purpose. Not just high hardness is important, but also toughness is also needed. So the toughness indicates the resistance to impact. So because the wheel is rotating at 3000 rpm and suddenly it comes in contact with the workpiece which is almost stationary. Okay, so definitely there will be some kind of the sudden impact on the surface of the abrasives. So if there is no toughness, then it will simply break like cast iron or break like glass, so it will not be able to perform any cutting. So toughness is important, resistance to impact is important. The fourth property that is really important for the performance of the abrasive is the friability. What is this friability? Is about the ability of the abrasives to get fractured. You see, under high stress conditions. So you see, initially you started with the nice abrasive like this. It had a sharp edges here and there, say. So gradually it will wear out. Okay, when it will wear out, to these sharp edges will be lost, size will be reduced. Okay, so when the size is reduced, material will not be cut, so you will be putting in more infeed, more depth of cut, so that the abrasive indents the workpiece and performs the grinding. But since it has lost its sharp edges, it has reduced, size has been reduced, so the load or the stress on the abrasive will be increasing. So in that case, the abrasives will get fractured. So if it doesn't fracture, then the cutting ability will continue to degrade very significantly, and the wheel may not be able to cut. So what is expected, as soon as the sharp edges of the grinding wheel are reduced, stresses start increasing, so these abrasives will get fractured due to the increased stress level on the abrasives, and the fresh sharp edges are produced. So initially, say it had sharp edges like this, so once it gets rounded off like this, okay, as soon as it gets rounded off, it gets fractured. Since it is hard, it is strong, and it is tough, as soon as it fractures, it again produces the sharp edges, fresh cut sharp edges. Okay, so the friability is about the ability of the abrasives to get fractured under the high stress conditions, so that the fresh sharp cutting edges are produced. This is one. The second, the abrasives themselves get dislodged. They get removed from the wheel, and the new abrasives which are under the surface, they get exposed. Say these are under the surface and these are present at the surface. Okay. So when their cutting ability is lost, if they are not getting fractured, so under the high stress, these may get removed. So the inner abrasives which are there in the subsurface zone of the wheel surface, they get exposed and they allow the cutting, they allow the grinding. So the fresh cutting edges are exposed. So there are the two dimensions related to the friability. One, the fracture of the abrasives producing the fresh sharp cutting edges. Second, the abrasives getting dislodged and exposing the fresh cutting edges again. So it is expected that the abrasives have these characteristics: high hardness, good wear resistance, good toughness, at the same time the good friability. Okay, and I have already talked about the kind of abrasives which are there, like alumina. This is commonly used for tough materials like steels. Okay, then silicon carbide. Okay, then the silicon carbide is used for machining of the non-ferrous metals, because it can interact, and it is also used for machining or grinding of the cast iron. Okay, so alumina primarily for steels, and the tough metals, silicon carbide for non-ferrous metals and cast iron. Then CBN, cubic boron nitride, this is used for machining of grinding of steels as well as grinding of cast iron. And as I said, the diamond is used for non-ferrous metals, ceramic materials, carbides, hardened materials. So carbide, ceramics, and the glass and other hard materials, non-ferrous metals, cutting of that is performed using the diamond. Okay, so that this is about the abrasives. Okay, now going to the another dimension related with the grinding wheel is the grit size. Okay, grit size, about the size of the abrasives particles which are being used for making the grinding wheel. Okay, so it is extremely important. It affects the grinding operation to a very large extent. Why? Because it affects the rate at which the metal is removed, so which is called metal removal rate. In simple term, in abbreviated form, it is termed as MRR. Okay, so in a big way, MRR is affected. If your material is removed rapidly, you will be getting there the desired tolerance, desired size, desired finish quickly. But the MRR is one thing and the surface roughness is another. Okay, surface roughness. So it is the surface roughness which is quantified, not the surface finish. Surface roughness is quantified in terms of the, say, RA, center line roughness average value, which is usually measured in terms of the micrometer. Rough surface may have the roughness, say, of 10 to 20 or more micrometers, and a finished surface may be like, say, 1 to 2 or even less. Okay, so 1-2 micrometer average roughness, this is, you can say, this is a very good finished surface, and this is a rough surface. But technically we measure the surface roughness: high surface roughness, low surface roughness. So this is basically the low roughness and this is high roughness. High roughness means 10-20 micrometer, Low roughness means 1 to 2 micrometer or 0.1 micrometer, like that. So that we call as a finish, otherwise it is rough. So we quantify the surface roughness. And surface roughness, that is usually quantified in terms of the RA and the and MRR. These two most of the time move opposite. These are opposite in nature. If you go for high MRR, surface roughness, in terms of the surface finish actually. So high MRR, high roughness. High roughness means low surface finish. Low surface finish. Okay. So if you want high MRR, then obviously you will be getting the low surface finish, or you will be getting high roughness. Okay. So low MRR, usually we get the low RA. So lesser metal removal rate means longer time it will be taking to get the desired tolerance and the desired finish. Okay. So what we want basically at any time during the grinding, MRR is high, material removal rate is high, but the RA is low. So this is the contradiction. We don't get normally both high MRR and low RA, that we don't get. So how and why we are not getting it? So if just to see this, let us see the different aspects related to the grinding. If you take abrasive of large size, or if you take abrasive of fine size, so abrasive maximum it can penetrate up to half of its size. So this will be the zone where from the material will be removed, and you will be getting the surface of this morphology. Okay. So this is the volume of the material removed, and this is the morphology of the surface that you are getting. So this is the depth of the scratch which is being formed. Okay. So earlier if it was the scratch was this much, now after the grinding you might have reduced it to this much level. Okay. So your roughness has been reduced, but still it is high. On the other hand, if you work with the finer abrasives, so this will be the zone where from material will be removed, and the scratch size that will be formed is just this much. So it is the fine that the depth of the groove that is being formed due to the grinding is fine. So here the volume of the MRR, in this case volume of material removed per unit time, is less. So MRR is low, here MRR is high, but the roughness, if you see, the depth is high. So RA is high here. Here RA is low. Roughness is low. So you will be getting this kind of the morphology. So average roughness will be low in this case. So so this is the case when you need the high MRR, you will be going with the larger size. If you need high MRR, then you will be going with the large size abrasives. If you need the low roughness, low RA, will be going with the fine abrasives. Okay. So now summarily what we can say, so small size abrasives. How do we measure the abrasives? And the small size abrasives therefore will be leading to the fine finish, means the low RA value. Okay. And at the same time your roughness will be metal removal rate will be low. So low RA and low metal removal rate will be offered by the fine abrasives and a small size abrasive, and the large abrasives, large size abrasives. These will be leading the poor finish, okay, high RA value, at the same time high material removal rate. Okay, so the things will be happening fast, but the roughness will be high in case of the high abrasive. So this is one thing. Apart from this, the roughness, the abrasive size also is used in a particular situation, in a particular way. Not just the MRR and the roughness is seen when we are selecting the abrasive of particular size, but also we try to see the workpiece material, the workpiece, what the workpiece metal is made of. Okay, so this is soft. Soft means like 50 HV or 100 HV, or it is hard, like cast iron or hardened steel, like say 600 HV or 1200 HV, like this. So the hard or the soft, which kind of material is to be smoothed or grinding is to be performed. So if when the material is soft, say this material is soft, so for the shearing by the grinding by the abrasive, shearing of the soft material will not be causing much of the stresses on the abrasives. Okay, so the load or the stresses acting on the abrasives during the shearing of the material during the grinding, okay, soft material. So if there is an abrasive working on the soft metal, so the stress which will be acting on the abrasive during the removal of the material by grinding, so that stress will be low. Okay, abrasive will not be break, abrasives will not break under the low stress. Okay, so on the other hand, if the large size abrasive if used with the hard metal, so in case of the hard metal, if under the identical conditions, the stress will be high. Okay, say if this material is hard, so the stresses will be high, and in that case under the high stress abrasives may break. So very frequent fracture of the abrasives will be taking place. So what we do basically, large if you use the large size abrasives like this with the hard materials, it will break very frequently. But with the fine size abrasives, even when working with the hard material, it will not break so easily. Why? You just see this cantilever effect. If this is the, say this is the component, okay, and during the shearing the stress is acting here, say this is the tool abrasive only. So in that case, when the size is large, the stresses are acting here. Okay, this is the size of the abrasive, stresses are acting here. In case of the soft one, the stress or the load is less, so it will survive. But when it is when the workpiece material is processed is hard, say when the workpiece material is hard, so the load is high. So when the load is high, stresses are more, this will get fractured easily. So large size abrasives under the high load means while working on the hard metal, this will be getting fractured easily as compared to the case when the hard materials, grinding of the hard materials is performed using the small size abrasive because of this cantilever effect. So in this case, when the abrasive size is large, working on hard materials, it will break easily as compared to the case when the abrasive size is small and working on the hard material. Okay, so in nutshell what we say, large size abrasives are used for soft metals only because they can sustain under the comparatively lower shear stresses which will be acting onto the abrasive. Okay, and the fine abrasives can perform or can sustain the higher stresses which will be acting during the grinding of the hard material. Okay, so the simple fine abrasives for hard metals and the coarse abrasives for the soft metal. One for fine abrasives for low RA and low MRR, and the coarse abrasives will be leading to the high RA and high MRR. Okay, so these are the three things related with the size of the abrasives. Fine abrasives for hard materials, for lower RA value, lower MRR. Coarse abrasives will be good for the softer materials, higher RA value and higher MRR. Okay. How do we check and how do we measure this? So abrasive size is measured or it is indicated using the grit size. Grit size, say just for example, is indicating in certain numbers. 20, say just for example I am mentioning 40, 80. So what is a grit size 20, grit size 40, grit size 80, grit size 140 or grit size say 170. So what it indicates, grit size is indicating basically the mesh size which has been used for screening the abrasives. So in 1 square inch area, how many meshes are there, like this? So if there are 20, okay, or if there are 40 in 1 square inch, if there are 80, so increasing the number, decreasing the size of the mesh. Okay, so decreasing the size of the abrasives that will be screened through these meshes. So the grit size indicating the number of meshes in per square inch. Increasing the grit size means decreasing the size, increasing the grit number means decreasing the abrasive size. I will write here in micrometer what is the meaning of the say grit size 20 means the 840 micrometer. So obviously for 40 it will be finer, say 400 micrometer. 80 grit size means 177 micrometer. 140 grit size means 105. There is no direct linear relationship in terms of the micrometer size and the grit number. It is related with the number of meshes in per square inch area, and for 170 say it is 88 micrometer. All right. So here this corresponds to the, say just for an example, size of the hair. This corresponds to the size of the sugar powder. Okay, and this say that's about 140, and say simple sugar grains, uncrushed sugar grains which are large in size, say sugar grains, simple. So this is just for having some kind of the idea. There is a whole range of the sizes. So basically the grits are further finer size are also available. So when we use the grinding wheel is using the grit size of 20 means very coarse abrasive, or it is using the 170 grit size, it is fine abrasive. Okay, and this in between you have the increasing grit number, reducing the grit size. Even you have the grit size of 400 grit number or 600 grit number. Okay, so the effect you have already seen. How does the grit size affect the grinding process? Okay, now these the grinding in a grinding wheel, the abrasive shape, see, there is no perfect shape, there is no regularity, so the shape is random in this grinding wheel. It is expected that it is sharp edged and not rounded, it is having the sharp corners. Okay, so the shape is random, there is no one or perfect shape. It is better, it is having the, it is irregular, sharp cornered and sharp, it is having the sharp edges. At the same time the distribution is also random, so the random shape and a random distribution. So where you may find like in one zone density is more, in another zone it is not that. So it may not be, distribution may not be perfectly uniform. It may vary little bit. And similarly, the angle of the abrasives which will be doing the cutting. So you can say the cutting angle is also random, so a lot of randomness exists. So the shape is random, distribution is random, and the orientation of the cutting edges is also random. For example, like say your wheel may abrasive may interact with the workpiece like this. So here cutting edge is inclined in this manner. Okay, so or the cutting edge is inclined in this manner. Okay, and interacting, or the cutting edge simply inclined in this manner. So here, so this is the edge of the abrasive which will be performing the shearing. This will be the edge of the abrasive which will be performing the shearing, and this is the edge of the abrasive which will be performing the shearing. So with respect to the movement and with respect to the surface, if you see, this is about say 90 degrees. So here the angle of this this is, you can say, rack face of the abrasive cutting edge. So here it is 90 degree, means the rack angle is 0 here, 0 rack case. Here the rack is positive and here rack is negative, because here, so the different the angles, the cutting angles which can be effective during the grinding can vary significantly from 0 to the positive to the negative. Okay, so random, so there is no optimum cutting angle in the grinding process. It can vary significantly. Okay, then you have that how this cutting happens, and how does the interaction between the grinding abrasives, the abrasives in grinding wheel and the workpiece interact. Let us see. So one simplest thing is this, where the material is simply removed by the abrasive in form of the chips like this. So the chip will be coming out in this form. Okay, so this is the workpiece, right? So this is the abrasive and this is the material which is experiencing the shear stresses and getting removed. So this kind of the action is called cutting. Okay, but when you see that the abrasive has been rounded off, okay, and the material is very soft and ductile, in that case the indentation performed by the abrasive is fine, but material flows sidewise under the effect of the stresses. So in this case, just the plastic deformation through the flow of the material sidewise is taking place. no removal of the material. It's just like you just press your finger in a wax, so the material will flow sidewise. Okay, if you scratch, it may come out, a part of the material may come out and perform that will be doing the cutting, but a part of the material may flow sidewise. So there is one situation where cutting is happening. The second situation of the interaction is the material is getting flown, getting displaced sidewise. So this is called plowing. Okay, plowing. Okay, and the third one is here, it is just the bonding material and the abrasive material. The two are very close to each other, no significant indentation is taking place. So here just rubbing is taking place, rubbing of the bonding and abrasive material with the surface of the workpiece. So there are three possibilities: cutting, plowing, and the rubbing. In these two cases, there is no removal of the material, but certainly the heat is generated due to the friction and the plastic deformation. To understand the heat generation in plastic deformation is simple. Like you take any aluminum wire and keep on bending it for 10 times, 15 times, and after some time certainly it will break. The moment it breaks, you check the temperature, check the surface of the broken wire, you will notice that it has become hot. Okay, so the rise in temperature is attributed to the deformation and energy being applied to do this, to cause the fracture. And certainly whatever energy has been consumed in shearing, part of that is converted into the heat. So heat comes from these three sources basically: the friction and the shearing or the deformation which is taking place. Shearing, cutting, the deformation, and the rubbing and or friction. So these will be causing the rise in temperature. To maintain the temperature within the safe limits so that the undesirable effects of the heat generation are not observed on the surface of the workpiece, then we will be doing this cooling, continuous cooling, or the coolants are applied during the grinding. So that was about the interaction only. Then there is the next aspect is about the grade. After the grit, there is a grade. Grade, I said, in a wheel you have the abrasive like this. Okay, so these abrasives will be held by the bonding material all around it like this. Similarly, the another abrasives, it will be held by the another layer of the bonding material, and this kind like there will be a lot of abrasives inside as well, and all these will be held by the abrasives, and in between also you will get some kind of the pores, air pockets. Okay, so there are three things in any grinding wheel. One is the abrasive, the second is the bonding material, and third is, you may also notice, air pockets that you can call as a pores. Okay, so whole of the grinding wheel will be made of these three. These we can say as, and each will have a certain proportion. Okay, so Pg will be termed as the proportion of the abrasives. Proportion of the bonding material will be termed as a Pb. Okay, and the proportion of the pores will be termed as a Pp. Okay, so the sum of all these Pg, Pg plus Pb plus Pp, proportion of abrasives, proportion of bonding material, and proportion of the pores. Sum of all these will be equal to 1. Okay, so when you see the bonding material, certainly it is important that there is a good bond between the abrasive and the bonding material. So how good it is, that is indicated by the grade or the hardness of the wheel. Okay, so it is about, so don't get confused with the hardness of the abrasive. So we'll use single term grade only. Grade indicates the bond strength, like this abrasive, how firmly it is bonded with the bonding material. So this bond strength is indicated by the grade. Okay, so there are just to understand, there is soft grade and the hard grade. Soft grade means this bond is poor, so the abrasive will be easily removed from the wheel in case of the soft grade. And hard grade means the bond between the abrasive and the bond between the bonding material and the abrasive is very good, so it will be termed as hard. So in case of the hard grade wheel, the abrasive will not be broken or get dislodged easily. It may get fractured, it may get rounded off, but it will not be removed easily. So in a way it is good, in a way it is bad as well. So so this is about the grade. The grades are indicated using the letters alpha from A to Z. A is softest grade and the Z is the hardest grade, and obviously somewhere M and O P Q, somewhere M is termed as the middle grade grinding wheel. Okay, so where what is used, now that is what is to be seen. So it is very simple, and let us understand the role and why do we say how do we say it. Like say this is the abrasive, okay, and this is the kind of bond. Okay, so when we are using the abrasive for grinding of the hard materials, okay, grinding of the hard materials, so hard grade means the bond is hard grade, means bond is strong and being used for grinding of the hard materials. So hard materials, it will be wearing out, fracturing very rapidly, but the abrasive will be retained by the bonding material. So what will be happening, your the abrasive size has been reduced significantly, like say it has been left up to this, its cuttability has lost, but still it is retained. So that will be happening in case when the hard grade is used for cutting of the hard material. Okay, so in this case dislodgement will not be happening, removal will not be happening. So it is good that the hard grade is used, especially when the soft material is to be removed, soft grinding of the soft material is to be done, so that the stresses acting on the abrasive will be less, its wear rate will be less, so the life of the grinding wheel will be long. Okay, so on the other hand, when we are so what we do for hard grades are used for the soft metals, soft work materials, and the soft grades are used for the hard metals. Why it is so? Like when the abrasive is grinding wheel is made of the soft grade, the bonding is poor, okay, and the workpiece is hard, so lot of stresses will be acting. So initially the abrasive will be working on the grinding wheel, but in meantime, as soon as it start, the abrasives will get deteriorated, they will get rounded off, stresses will increase. So as soon as the stresses increase, the abrasive is dislodged because the grade is soft. So the fresh abrasives will be exposed. Okay, so so this is the advantage of using the soft grade with the hard materials, hard workpiece material. Like hard workpiece material will be damaging the abrasives rapidly, increasing the stress level, which will be causing the rapid dislodgement of the abrasives from the wheel. So the fresh abrasives will get exposed for performing the cutting. So that is why what we recommend, soft grade hard grade for soft material, and hard grade for soft grade for hard metals. So just opposite, hard grade of the wheel for soft metals of the workpiece, and soft grade of the wheel for hard workpiece materials. Correct? Okay. So